Okay, I am now going to do an example of a two-tailed test. So this example is going to go a lot faster than the first example I did because I won't need to introduce all the steps and the logic behind the test. What I'd like to do is just write down what you would need to write down when doing the test, and you can see how smooth and easy this procedure is, and it really flows quite nicely, and it makes a lot of sense when you get into the groove of performing a hypothesis test. So in this example, it says that the average class size 5 years ago was 24 students. And now to see if this has changed, a sample of 35 students is selected and has a mean of 25.6 and a standard deviation of 4.2. So what we want to do is test at alpha equals 0.01 whether the true class size is different than it was 5 years ago. Okay, so now the key here is I'm not necessarily wanting to show that it's greater than or less than. I'm just wanting to see if it's changed or not. Okay, and when you perform a test, you should set up the hypothesis before you actually draw out the sample here. Okay, so you don't know what the sample mean is when you set up the hypothesis. So when I'm deciding I want to test, I don't know if it's bigger than or smaller than. I just want to see if it's changed in the past 5 years. Okay, and so I'm going to test to see if it's different than. So to set up my hypothesis here, the null hypothesis will say it isn't any different. It hasn't changed. It's the same that it used to be. So that 24 there, what it used to be, is the hypothesized mean. Okay, we don't know what the true mean is. We want to test to see if it's different than 24. So the null hypothesis is going to say that the true mean is no different. It's the same as what it was 5 years ago. So the true mean is equal to 24. And then the alternative is the competing claim, and this is I want to show that no, maybe it's different than it was. And so this is going to be the true mean is not equal to 24. So the null will always be an equality. The alternative will always be an inequality, either less than, greater than, not equal to. All three of those are inequalities. So the null will always say there is no difference. It assumes it hasn't changed, it's the same. And then the competing claim is no, I want to show that it actually is different than 24. So that not equal to makes this a two-tailed test. So when I set up my hypothesis here, I have to shade a little bit on both tails, like this. Okay? And then my alpha is equal to 0.01. So this is a two-tailed alpha, 0.01. So I go to my t-table, I go to two-tailed alpha, 0.01, and that ends up being this last column. And then I go all the way to the bottom to get the critical z value, and it's 2.576. So this is 2.576, and over here is negative 2.576. Okay, so you have the negative and the positive. And these two are the rejection regions. So the idea is if you're less than negative 2.576, you're going to reject H naught. And if you're greater than 2.5, a positive 2.576, you'll also reject H naught. But if you're in between the two here, that's when you're going to fail to reject H naught. Okay? So one way of thinking about this is if the true mean was equal to the hypothesized mean, you would expect the test statistic to be very small, close to 0. So the closer it is to 0, the less evidence you have to reject H naught. But the further out it lies, the more evidence you have to reject H naught. And in this case, it could lie out either way, and then these are kind of your criteria. Once you pass those into either tail, then you have enough evidence to reject H naught. So now we need to calculate our test statistic to see if we have enough evidence. Okay, so this is the sample mean, which is 25.6, minus the hypothesized mean, which is 24, divided by the standard deviation, which is 4.2, over the square root of n, and that's 35. Okay, so plugging this in my calculator, I get 25.6 minus 24, hit return, divide this by 4.2 over the square root of 35, and that bottom is in parentheses. And I get, in this case, a positive 2.25. So now I need to compare this to my rejection region, and this is actually less than this. It would be like right here, and that means I'm in the fail to reject H naught. Okay, so my decision here would be fail to reject H naught. So this particular sample here did not give me enough evidence to reject H naught. Okay, so how do I make my decision? Okay, well, what we saw last time is whenever you have enough evidence to reject H naught, you would say there is enough evidence to conclude the alternative. But if you fail to reject H naught, you would say there is not enough evidence to conclude the alternative. So since I failed to reject H naught, I would say there is not enough evidence to conclude. And I wouldn't say conclude the alternative, but I would state what the alternative says. And the alternative is saying that the true mean is different than 24. So there is not enough evidence to conclude the true mean is different than 24 students. So in this case, when I drew out this sample and I performed at this significance level, there was not enough evidence to conclude that the class size has changed. So that would be an example of a two-tailed test, and also this is a pretty low significance level. 0.01 is more significant than 0.05 that we did last time. So this is actually requiring quite a bit of evidence. See, these tails are further out, and so this has to be further out before you can reject. Okay, so this is a two-tailed test, and in this case we did not have enough evidence to conclude the class size has changed. So in this third video, we are going to look at a right-tailed test.